Please give a warm welcome to Dr. Phil Root.
Good morning. I'm fortunate to hail from the Strategic Technology Office. And in the Strategic Technology Office, we look for those capabilities that yield exponential returns, are the most impactful. In what ways can we yield the greatest impact and change within the innovation community and really for national security? And so as you look at our portfolio, and as we've discussed in the past, we look for and we believe there are opportunities within command, control, and communications that when implemented correctly can stitch together a variety of assets that yield far greater impact than any asset on its own. And so we lead a discussion about systems of systems, and increasingly about systems of autonomous systems that allow us to perform a variety of functions like collaborative sensing, centralized and decentralized decision-making, as well as collaborative effects. And the intent of the graphic is to demonstrate the power of homogeneous and heterogeneous teams, but importantly, and relevant to our conversation here, we ensure to put the human inside the system boundary, to ensure that we have human-centered design, because that is key to some of the asymmetric approaches that we see. And so as we discuss systems of autonomous systems, I think it's appropriate for us to talk first about the autonomous systems themselves, the platforms, and then some of the nuances and important challenges associated with putting the human inside that system boundary. And then finally, we can build on that foundation and talk about some of the desirable emergent behavior that comes when you have systems of autonomous systems, but also some of the challenges when that emergent behavior is not aligned with a broader intent. So I've been fortunate to have this conversation over a number of years, and it's been reinvigorated since our panel members arrived here, dinner last night, breakfast this morning. And so I'd like to include you in an ongoing conversation that I've been fortunate to have with our panel members here. I consider them mavericks, as Captain Weed referred to thought leaders. Consider them thought leaders, but importantly, truth tellers about the true ability of autonomous systems and the readiness of autonomous systems to serve as a platform for us to explore asymmetric approaches for national security. So I'd like to invite our panel out. The first person I'd like to introduce is Dr. Matt Johnson. Matt started his career as a naval aviator, and then while in the Navy and thereafter earned his degree from a number of places, Notre Dame and Delft. His thesis on coactive design I consider to be required reading for anyone that's serious about human-centered design, human-machine teaming. He is currently at University of West Florida and Institute for Human-Machine Cognition, or IHMC. Absolute thought leader and truth teller about autonomous platforms, but importantly, human-machine design and human-machine systems. Next, Dr. Tim Chung. Tim and I were quote-unquote office mates on the 10th floor in TTO. I say air quotes around that because we were never in the same place at the same time. I walked by his empty office often as he would be in the field routinely beating on autonomous platforms in the Offset and the Subterranean Challenge. Prior to his stint at DARPA, he was at the Naval Postgraduate School. Now he's at Microsoft as Director of Strategic Missions and Technologies Division. And then Nick Radford. Nick joins us. He is the founder, president, and chief executive officer of Nauticus Robotics. Nauticus Robotics explores autonomous systems from the sea surface to the sea bed, exploring missions for climate change and to make a global impact. Prior to that, he was a principal investigator with NASA on humanoid robotics, such as the Valkyrie and Robonaut, destined for the International Space Station, as well as inclusion in the DARPA Robotics Challenge. So great to see you again. If we can restart the conversation, one thing that we've been talking about is autonomous platforms and the difference between what we see in one domain and the challenges of seeing success there and challenges elsewhere. Nick, do you mind starting with some of the challenges you see when you celebrate your peers in one domain and then you try to take that to the underwater domain and don't see the same level of
Sure.
success?
Thanks for the easy question to start the conversation. Wait, I mean, there's something in like the software community called the planning fallacy, where it's like, hey, we've done some things like this before. Let's try to project how this might be accomplished in a slightly different way. And let's try to put a schedule behind it and try to put a budget behind it. And I've been learning something called the autonomy fallacy. And it's like, oh, we've got self-driving cars, you know, for limited periods of time. Maybe they can sort of have a, you know, some few basic self-directed motions and behaviors. Let's apply that whole concept to how we're going to do stuff underwater. And quickly you find that all these chunks start breaking down, and even the way that the data available to you to create your fancy neural fuzzy fractal genetic atomic chaotic algorithm that works beautifully well in simulation, as all simulations are doomed to succeed, breaks down a little bit in the real world, especially across a different domain. So it's something I've been focused on for quite some time. We took a lot of spaceflight principles on how we were doing autonomous systems development, and at least had a fairly stronger analog putting them underwater, but came with its own very separate challenges. And so I think it's very important that we're honest with ourselves that just because we see some success in a domain, that there's a whole lot of stuff we haven't thought about in the other.
Yeah, and the challenge of communicating success in one domain requires a conversation about the metrics of that domain, the complexity of that domain, because what you can do with a drone, for example, in terms of mobility, does not relate to a different domain where just mobility is more challenging. Bipedal robots come to mind, for example, and particularly teams. But you've been beating on robots for a while. Do you mind sharing some of your stories?
Sure, yeah. It's hugely complicated in understanding the dimensions that go across this space. There's the platform dimension, which Nick has been talking a lot about. There's the environmental dimension of how complex is the environment you're doing. There's a networking dimension. A lot of this stuff has to interact through a network and support for that. And then there's also the mission, the complexity of the mission itself. You might have a simple environment and simple platforms, but if the mission is hard enough, that also adds complexity. So each of those dimensions, you can't consider them, you know, individually. Any one of those dimensions could make your particular problem challenging.
Yeah, it's like your discussion, your swarm definition that you used, describing swarms and offset, if I recall.
Yeah, I think Matt said it well. There are just so many dimensions, and trying to be able to transfer from one problem set to another, you need to get crystal alignment on all of those if you're going to have any hope of having that transfer. And I think you were saying it, Nick, that the ability to take space lessons and apply them to underwater, there must have been some alignment in some angles, but certainly not in others. And I think looking at swarms of robots, I think that was one of those lessons learned. Just because you can have light shows doesn't necessarily mean you can have swarm technologies capable for urban mission sets, as an example.
Autonomy versus automation.
Right, that's an example.
Yeah. Nick, you've really helped me understand some of the challenges of communicating autonomous capabilities. When you said there's, the right way to look at it is you can demonstrate, say, the 5th to 95th percentile of the environment, but you really have to essentially live in the field in order to push between the 0 and 5 and the 95 and 100.
Oh yeah, I mean, there's a long discussion to be had around the system level development and then getting it out into the field and actually testing it, which is, it's funny to me how long we'll spend in developing an autonomous system. And my electrical engineers, or rather my mechanical engineers, will take 50% of the schedule, and the electrical engineers will take the other 50% of the schedule. So I'm already, you know, at my limit, and then the software engineers want to take 100% of the schedule, right? So I'm already like, you know, 100% over budget. And we haven't even got to the application and autonomy side. And so we'll spend all this time just to put it in the field and the connector breaks, right? And it's incredible the lack of true testing that goes in to try to suss these things out. Like on average, about 25% of a schedule is toward testing on any kind. And I think as these systems become more and more complex, because these things are exponential, it's not linear, right? We try to linearize these ideas in our head, but when you start layering systems on systems, especially when they have autonomous behaviors, which by definition have some emergence to them, which is another way of saying crap we didn't think about. And so there's just this whole level of uncertainty, right? And it's like, how do you even test for it? So not only do we have a fraction of the testing budget that we probably should have now, but it's going to be far more dominant to really qualify these systems. And I deal in sort of both domains. I think I'm very proud of part of my company is we have the sponsored area where we work with DARPA in some areas, and then but we're also trying to commercialize the technology. And the government's a great place to sort of explore that, because they say, hey, that didn't quite work right. Here's some more money. Try it again. The corporate side, they have less tolerance for that. Yeah. But nobody thinks about the extent of testing required.
Yeah. Yeah. And you gave 25% as a number. I think that's way high. I think most projects and programs that I've seen are way less than 25% testing, especially if you focus on the actual user and operational testing. I think that is such a fraction of what it needs to be to do this effectively.
Yeah. Yeah. Staying in the field is hard. I love the way you described you're forever testing. Walk in, and I'll let you complete the story. You walk in, or your DRC stories of you would get a carpet and vacuum, and it wasn't part of the task. Go ahead.
Yeah, so the DARPA Robotics Challenge, if you guys remember that from a couple of years ago, had 6 known tasks, driving and turning valves and stuff, and then it had 1 mystery task. But it had 3 years where we got to see several mystery tasks, so we kind of got to know what was coming. However, we didn't want to limit our system to that. So part of what we did internally was every day I would come in with a new challenge. I'd go to the hardware store over the weekend, find some toys, and I'd bring them something to do the next day. I brought them a vacuum and a carpet. I brought them a shower head to assemble. I just brought stuff for them to do as a way to investigate how flexible and complicated can we make this system? How much can we do with it? I didn't want to just push for what the DARPA Robotics Challenge was asking us to do. I knew we could go beyond that, and so that pushed our autonomy, it pushed our engineering, it pushed the human integration, it pushed the operator interface, it pushed every aspect of it by constantly challenging yourself to kind of broaden the range of what your system is capable of handling.
Yeah. I mean, to piggyback on that, I think the challenge for the DARPA Robotics Challenge gives you the opportunity to go not only on the system side, but also on the human and training side. Becoming field operations savvy is something that just takes a lot of testing to be able to do that. And I think the lessons that you learn in the field, that's the hard part to transfer, I feel. I'm curious to know if there are easy ways to transfer the lessons learned of, example, Sub-T Challenge, we're in the middle of a cavern and it's humid in caves, and who would have thought? And so teams were getting hair dryers out of their hotel rooms to dry their embedded boards before their runs, and you would not have tested that, right? And the thinking that goes to, and so the next time they go to a cave, maybe they'll have thought through that, but that's the kind of lesson learned that I don't know how easy it is to transfer.
I mean, autonomous systems are, by definition, gaining knowledge during an operation in the field, trying to make decisions on an environment that is complex and typically not known a priori. I mean, really, what could go wrong, right? It sounds perfectly posed, but yeah, it's fascinating, and we wrestle with it a lot. And it's something that we reflect on all the time, because in the maritime domain where we're at, you could probably draw this curve where ground is easy to iterate on, aerial is a little harder, marine is just like a whole nother level, and then space is way up here. And in order to affordably qualify these systems and test them, we have to come up with analogs, because, as you said, Matt, even though the reference I read said 25%, I also raised my eyebrow and I said, "There's no way." Right? No way. Like we test the night before the demos due, right? Yeah. And I have this cardinal rule, which is never build a robot and test it and demo it to the customer in the same year. Yeah, and somehow I'm breaking that right now.
to great effect.
And there's lots of different learning involved in that, right? There's the learning of the automation itself, but there's learning of the engineers. Like the engineers getting out in the field and actually testing things is huge. And we've had discussions about how, especially new engineers who haven't actually gone and tested things are kind of blind to the problems they're going to see. And so getting them out in the field is valuable for their training. You know, systems developers, interface designers, operators, all of the mix. There's a huge value to being in the field and testing in mission context.
Yeah.
I think to that point, sorry Phil, but we have this expression that it takes 2 people to teleoperate a robot, and it takes about 10 of them to operate it autonomously.
Right.
And so just because you're going to put an autonomous robot in the field doesn't mean your engineers aren't coming with it.
Right. 100%.
And some of them, it's quite shocking when they know they have to be out on a boat for 3 days. We've literally had mutinies of like, we're not going out on a boat for 3 days. I'm like, you work at an ocean robotics company. Right. What are you talking about?
Yeah.
And looping that into the systems of systems, I mean, that's where you find the problems is the boundaries between those things. Like the operator interface people didn't realize they were going to need to deal with humidity, fogging up their camera or whatever, right? And it's really those boundary spaces that the field tests help expose.
Yeah. And we were saying that when you go from a platform to a system of platforms, whether homogeneous or heterogeneous in capabilities, it's not merely stitching them together, but really it requires a re-architecture, an ability to rely on other assets in a way that wasn't intended in the original design. And so it's actually incredibly challenging to set expectations, because you can see individual platforms doing something and you want them to do it together. And you can hack that, but you can't actually get an exponential increase in adaptability and speed unless you take the time to start over.
Yeah, I agree with that 100%. I think it's kind of an illusion that people buy into, that you can take a bunch of pieces designed independently and put them in the same room and hope they work together. You guys all came together, but if I asked you to play basketball, you may not be the best team out there because, 1, you may not have played basketball, and 2, you've probably never played together before. But that's kind of what we're asking when we put our systems together in one room or on one mission field and expect them to work. They've got to be designed, built, trained, whatever. All those elements have to be in there to ensure there's adequacy to support the interdependencies that are going to emerge as you try to work these systems together.
Yeah.
Yeah, that reminds me of, I forget which Olympics this was, but the Dream Team. You assembled all the star players in the National Basketball Association and put them on one team. And in their own right, they're dominant in the sport, but trying to put them together just didn't work so well. And I think part of it is what you were saying. You need to train together and learn and co-evolve together.
Didn't they lose to Lithuania?
Not going to comment.
But when you create a team, you're hoping for that team magic.
Yeah.
And one thing our discussions have framed for me is you want that magic, but you don't define the magic. So rather, we tend to give a use case, but that use case doesn't require the magic necessarily. In the absence of defining what a team means, you can absolutely hack together individual platforms that can appear to be working together, but you'll never see the emergence of a true team magic. So you really have to start over, but you have to, within the guardrails of what a team means, which has challenged my, I've always thought, let's just throw out a challenge. And you really can resort to a lowest common denominator in the absence of defining what a team means. You had been commenting on the lack of definition of what a true team means. Do you mind?
Yeah, sure. I mean, you get what you aim at. And so if you can't clearly articulate what an effective team means, you can't expect people are going to design to it. They're going to design to what they can do, and then they're going to try their best to label that as the thing you were asking for. That's just the nature of people in general. Yeah. But I think we have plenty of good examples in the world of what good teaming is. We have plenty of research that's been going on for decades about what effective teaming is. We're just turning a little bit of a blind eye to that as we go into autonomous systems, and we say, we know we want that, but we don't know how to do it, so we're just going to label waypoint following as teaming. That's not really teaming, right? There's got to be more to it than that. And so, but until we articulate the ground rules for what actually works and counts as teaming for effective progress, it's going to be hard to hit the mark.
Yeah. Do you think it's a lack of our ability to measure what good teaming is? Do you think that's where, either more math or other types of system engineering approaches would help us?
Somewhat. I think teaming is a big, broad concept, right? So as you combine these systems of systems and you want them to be more effective in team, that could mean a lot of different things. And so there is probably no one answer. There's going to be several answers, and so you need to come up with your own rubric of what counts as teaming. Once you have the rubric, I think the measurement will come. It's really hard to put a measurement system together in place without a rubric of what you're measuring. So I think there's the challenge. And even with a rubric, teaming itself has been very difficult and elusive as far as measurement goes. We've got team performance measures of speed and error rate and those types of things. But everybody knows that's not the right answer, the complete answer, right? Because you'll watch that good soccer team or that good football team that you know should win, but they don't. And then you've got all the Monday morning people explaining why it didn't work. But if we could have measured it, we would have been able to predict it, but it's tough to measure. And so putting good measures on teaming is difficult, especially to capture the team processes and remove the confounds of anomalies in the world or lucky guesses and things like that. It's so integrated, it's tough to tease apart, but not impossible.
I think there's two dimensions, right? So within the team, it's the autonomous functioning of one independent agent that then is wrapped up into a bunch of dependencies towards an objective, right? Kind of like how a football team works, but then the wide receiver is making some individual choices, right? And that's far different than a track team, which are almost independently, doing their own things, but yet it's toward a common objective. And so I agree, it's like trying to define teaming and then add some robots into it is even more complicated.
Yeah. Yep, and there's work in this area from the human side of the equation, right? There's people like Steiner and others who've broken apart different types of teaming tasks and they characterize the nature of that work. And I think we should be leveraging that to understand the difference between an ISR foraging basic task and a building clearing task. Those are fundamentally different. The way you team is different. The skills, behaviors, and techniques you need to use are different. But we sometimes treat them as if they were the same thing, and then we try to apply measures to them as if they're the same thing.
Yeah, you were saying you've seen hundreds of design documents or schematics for human-machine teams, and the human is not in the system boundary. Right?
Yeah, that's a huge problem in systems of systems design. I challenge you to show me a system or a system of systems that doesn't have people in it. They're there. I challenge you to go find me an equal number of engineering diagrams or architectures that have that human in the picture somewhere. We had the human domain conversation earlier today, but that shouldn't be a separate branch of research. Your system is a mission for people. It's trying to achieve an objective for people. And so that end user and that mission should be involved from the beginning in the engineering process. And how do you model that? How do you include those as engineering requirements? It's often lacking.
Yeah. Tim, you tangled with that.
Yeah, I mean, as Matt and Nick were talking about the human element, I think one of the key things from our lessons learned in our field programs was the human can definitely be an enabler. The human has the ability to do really rapid object detection and classification and all those kind of higher level tasks, but they're often also a limiter. And I think there needs to be an understanding, just like we want an understanding of individual robots in our team, we want to understand the limitations of the human as well. Mm-hmm. When we had robots going into underground environments, the teams were told they only can have one human supervisor. That was a constraint. And the teams would come back and say, oh, can we have two? Can we have three, right? Because we want somebody to focus on this subsystem or things like that. And I think constraining it to just one kind of quantified for us the role of that one human, which again goes back to metrics, like what is the value of that one agent in terms of contributing, whether it's a robotic agent or a human agent, what's the value? And I think finding ways to measure that are continuing to come a long ways in still existing research, but there's still a lot to do.
Yeah, yeah. Nick, anything to
add? What we focus on is fundamentally the relationship between the robot and the person. There's some really challenging problems, and you want to push the autonomy as far as you can go, and then you have a business, you're trying to make money, and you'll cheat as much as you possibly can, right? And so we sort of have like more like this teleperception. Instead of letting the robot sit there and stare at the door handle wondering if it's a butterfly, we just sort of tell it's a door handle. And humans are incredibly good at reading lossy, compressed information. So what we've been looking at is how little information can you transmit back and forth, and then how do you increase the time that the self-directed or the self-sufficiency of the platform can be on its own. We get the benefit of working underwater where the dynamics are relatively slow. It's not like watching two F-16s in a dogfight. But however, the communication methods are equally slow. We have about 1,500 meters per second underwater, and bits are, it's more like dial-up networking, 1988 maybe. So it's really apropos. But it means that your robot and your operator have to be really well in tune with each other. In fact, we reference a ton of Matt's work with coactive design and have studied it intensely, because if you don't design with that sort of symbiotic feeling, you get rather opaque architectures, and that leads to failures.
Yep. And it's funny that you call using the human cheating, because in a team, you want to use your teammate. That's why they're there, right? If I have a co-pilot who does nothing the entire flight, it's not super helpful. You want that co-pilot to be of value. And so taking advantage of your teammate, whether it's a piece of automation or a human being, is the right thing to do. Now you have to do that with what Tim was pointing out, is there are constraints. How much you can interfere or intervene or grab attention, there are constraints, and you've got to live within the bounds of constraints. But this isn't an optimization problem, teaming.
Yeah.
It's a maximization problem. I want to use my team as much as possible within the allowable constraints. I don't want to minimize the use of my team. So I think that's where we kind of sometimes go astray, is we are so used to optimizing and minimizing. Let's remove as much of the human involvement as we can. I would say maximize the human involvement. We're an extremely valuable resource to the autonomous systems. Use that within constraints. One operator.
Yeah, I think there's an interesting split between here. There's this notion of neglect tolerance. How long can our systems tolerate not having some human helping it out? There's a flip side to that, which is neglect benevolence. And this is, how long will the robot benefit from not being interfered with?
Yeah.
And so I think that gets even more so complicated when you have teams of systems trying to operate. I think there's a desire for humans to want to know what's going on, have situational awareness of what these robotic teams are doing. And sometimes that means we have to go in and poke around a little bit more. That we want to go around and poke a little bit more. But I think there's an open question as to when or how frequently you want to do that.
Yeah, could you tell the story of the team that was trying to balance come back in the case of lost autonomy or lost communication, and the other said, but that's great, don't come back?
Yeah,
right?
Yeah, exactly. I think in the Sub-T challenge, it was often the case where robots would go off with no communications back to that single human supervisor. And there was a tension I overheard the conversation on one of the teams. The autonomy lead was just send it, like let it live out there for as long as it could, even without comms, so that it can go and do its task, which was doing an underground scavenger hunt, underground basically. Whereas the robotics core team, right, they were nervous about the mobility. They were thinking that these robots are going to topple over and it would just be a dead robot. We need to hear from it so that we know to redeploy it if necessary. And so there was, leave it out for 30 minutes. No, we want it back in 10 minutes. This is the lost comms protocol.
Yeah.
And finally, they settled on 22 minutes.
22.
Right, somehow. There was some weird compromising that went on there. But they were willing to let the robot go and wander around for 22 minutes in the absence of comms, and again, magically they discovered 22 as the number.
That's hilarious.
I'm exploring these concepts with my 3-year-old right now. 22 is a little long.
Yeah. Exactly. Nick, I mean to ask you, we've been talking about putting the operator in the box, in the system boundary, but you do a lot of field testing. Do you put your field team, do you just architect your field team in those interfaces intentionally?
Wow, that's a good question. Not especially well. There's sort of like this understood necessary reality that we forget about, and we need to be better at it for sure. I mean, they're an integral part of how testing gets done. Like I said earlier, it takes 10 people to run a robot autonomously,
Yeah.
right? And it probably takes 20 of them to test it autonomously offshore, and we don't consider that enough, and something we should improve.
So I'll go ahead, Tim.
Well, I was going to follow up, Nick. If you could design the DARPA program and figure out how to inject experimentation or testing in there, I mean, what would look?
Probably not the forum.
Okay, never mind.
No, I mean it just. I deal with the realities of the concepts that we come up with and we think we can do, and we try to demonstrate them. It's just there's never enough time for testing, right? There's never enough budget. There's never enough time. I think having that open and honest conversation about what's our end objectives. Let's not try to do 5 DARPA programs in one. Maybe we try to say we should be a little more measured with the rigor and the hardening, as we were saying earlier, of the thing we're trying to base all the functioning on. But I almost think we could really just refocus and redouble efforts around how essential a good V&V and testing is, because then we get into the fun stuff, right? But then we get into the mission objectives, and because that's a whole other animal as well. Mm-hmm. I mean, autonomous systems are indeterminate, right? These are something that we can only understand the edge cases through the operational, right? Well, in order to really get the benefit of that, we have to have stuff that's reliable. Yeah. And we just try to all sometimes smash it all into one, and then we say, oh crap, it didn't work. Why didn't it work? Well, because the connector broke again.
Right. This conversation is going to continue for a long time. Unfortunately, our time on stage is limited. So I'd love to have any questions that we have from the audience. The QR code is there. I'd love to hear from you. Question I've been exploring, are there alternatives that perhaps would allow us to move beyond the typical verification, validation approaches that we have, that we've seen so far?
Well, I think stop modeling them off of the way that we test non-autonomous systems, right? I mean, I think we always start with what we know, and we use that as a framework, but autonomous systems, which are quite exponential in nature, they take a reimagining of how to really verify. And I think we try to base too much of that roadmap on the way we would do non-autonomous systems.
Yep. I would also throw in there that V&V of autonomous systems often refers to literally the autonomy, the computational component. But as we're pointing out, there's a human-centered system here. There's a human in the mix. And V&V of human systems is never that easy. And so even if you can V&V and do the math on the autonomous system, which you should still try to do the best you can, extending that to include the human makes it a lot more complicated. And so we need other ways to do that. Fortunately, we've been V&Ving human systems for as long as we've had humans, so there's ways forward. Yeah,
but V&V of human systems, we can rely on a degree of graceful degradation, meaning if a human system doesn't perform up to some standard, we don't have the sense that they're going to be completely brittle and fail in a way that many of our robot friends do.
That's a very good point. That's a very good point. It's a very big distinction between the two. And so I think that's what the computational V&V is really getting at, is how do you protect us from those brittle points that you can't see.
Next question. Discussions on autonomous systems can tend to avoid discussions on the nature of meaningful human control. What is your experience with designing joint human-machine teams? We've explored some of this. Tim, do you mind commenting both? Really, we haven't talked much about offset. And through offset, you explored human-machine teams, but with a particular mission, and that mission was always changing because you architected it that way in the program. Your thoughts?
I mean, I think what was fun, fun in air quotes first, about the offset program was in how we solicited proposals. It was, yes, we want to advance swarm autonomy, but also want to, in parallel, equal partner was advancing human-swarm interactions. And the balance between how do you do swarm autonomy and also think about human interaction there was a key piece of the program. One of the kind of the questions of like, if you could, the reason we targeted large-scale swarms of hundreds of robots, air and ground, was because we didn't want to start with 1 or 5 or 10 robots and then try to extrapolate from there. We kind of needed to wipe off the whiteboard and start clean sheet to be able to think about what the human's role is in this context. And what we discovered was there isn't just one role for the human. It depends on if you're sitting back at the headquarters, if you're running around with drones and rovers flying and driving around you. That's a very different type of interface. And so we needed to straddle that. And the way we discovered it was in testing, right? You go into the field, and yes, you need to be running around with drones flying overhead, so you need a different way to present. So maybe augmented reality turned out to be an interesting way to get that information quickly. But if you're back in a protected location, that's a very different kind of a mission planning type of a model where the human gets to be integrated. And I think, as was mentioned earlier, it's really about that mission and operational context, and then testing again, and then breaking things and then testing again, where you get to exercise the kind of the merging of the human and the machines, specifically in the team context.
Yeah. Nick, you have a unique position in that you have corporate customers that are distinctly different than government customers. Do you find that your system, when you put the human inside that system boundary, has to have two archetypes, a government operator and a corporate operator?
Yeah, I mean, on the government side, it's how do we lessen, or rather, how do we minimize it all the way to zero? And a lot of these missions are long duration, autonomy, exploration. How long can it go without being interfaced with? The corporate side is the exact opposite. They want to understand that someone has purview and an agency over this item, and it's going to be doing things for a few seconds, but you can stop it, right?
Yeah.
And like, well, not unless we violate some physics, and it's tough because it's this unfortunate paradox of your cake and eating it too. We know that in the commercial sector, we will significantly reduce operational costs through a judicious deployment of autonomous systems. That is without question. It's getting over the regulatory hurdle and being able to prove that they are capable. I mean, it's actually why I recently put someone on my board that is an assured autonomy, right? I mean, even at the board level, I want to have these discussions because they will be so integral to how we go out and commercialize these technologies.
Yeah. Matt, next one's for you. Using the human brain as a coprocessor for augmenting autonomous system capability seems powerful but undeveloped. Are there new capabilities or fundamentals that deserve investigation? In all fairness, Nick gave me $5 not to ask him that.
Yeah, I can see why. So I am not a brain expert, but I work with some. And I did stay at a Holiday Inn, so I'll give it a go here. So if you're talking about physiologically measuring brain signals, that's one thing. We've been doing or trying to do that for a long time. DARPA Augmented Cognition, which I was just a code monkey in my youth doing that one, was a fun challenge of actually measuring the physiology of the brain, detecting signals, and trying to do something useful with it. That is still ongoing. That's not my work, but I've been reading up on people who are doing that. I'm not convinced it's ready for prime time yet. But broadening out from the general specific discussion as a brain as a coprocessor, I would argue that is what teaming is. As a team member, I am coprocessing everything. My co-pilot sitting next to me in the airplane is a coprocessor. We're not measuring him physiologically. We have natural language and other interfaces to interact with, but we still work as a coprocessor, if you want to call it that. And so I think there's ways besides direct physiological measurement that we can sort of get at that. And I think teaming is a perfect metaphor for that.
Last question for you all. I'd appreciate giving you the chance to reflect your thought leadership, but also your reflections on reality. I consider you all truth tellers as well to our conversation this morning. What are some of the challenges as we approach systems of autonomous systems? But if you can couple the challenges with the opportunities, what could we be doing as a result of new directions? Nick, I'll ask you.
Nice.
I mean, what quickly comes to mind, and I feel like I sound like a broken record, but funding is a big deal. Just the honest conversation about how much it actually takes to try to make these advancements. I mean, every real progress will tend to overreach, sort of pull it up. But it's also highlighted in just more generally in society, just some quick stats, and we deploy about 170, 180 billion dollars in venture capital money in the U.S., and 60% of that goes to software-only software-only companies, and 32% of the rest goes to kind of financial, healthcare, consumer-facing. 8% goes to anything related to platforms or industrial technology. And what we inextricably confuse all the time is that we have this platform morphology and its capability, which we call autonomy. And I know this might be sacrilegious, especially in this crowd, but this autonomy in a box idea, it's like it's so hard to wrap your head around because it doesn't scale across platforms. We're not even thinking on that level yet. And I mean, if I downloaded Peyton Manning's brain into mine right now, I'm not going to be a Hall of Famer, let alone an NFL quarterback, right? So we just, and I think that what I said about earlier about funding is reflected also. We sort of, we kind of fund in groups, and it's all related to software now. We think we can turn everything just crazy intelligent just by throwing a few little bits at it, and it's the platform, the maturity of the platform to even to deploy the capabilities we're contemplating that the software can do. It's a tug of war, it goes back and forth, but overstressing the de-emphasis of any type of platform is, I think, wrong in my opinion.
Yeah, I could probably piggyback on that as well. Just from experience, I'd say DARPA is really great at identifying feasibility proofs. That we want to build an existence proof of a capability, but that doesn't necessarily translate to resiliency proofs, right? Like it doesn't say that it's going to be reliable every time you go out there. And a good part of that has to do with the fact that when we're dealing with physical hardware-based systems, only 8% of that capital is going to really putting a value on experimentation and hardware. And I think that translates, whether it's in DARPA or elsewhere, this emphasis on the translation between autonomy being software, and I know there are probably many in the audience that say autonomy is purely software, and I think we've been highlighting that no, it includes field lessons, it involves people, involves a lot of other things, and being able to articulate that in both from investment or government funding, I think is probably something that's helpful, but also an opportunity to be able to tease out, hey, here are the real hard nuggets on, let's say, the hardening of robotic platforms, as an example.
Yeah, thanks.
I'm going to go down a slightly different road. I think one of the biggest impediments is this bottleneck we have that, as we mentioned earlier, it takes 10 people to run an autonomous system. That is a huge impediment. These things were invented for efficiency and reduced manning and lowering costs. It's done none of that. There's zero data that supports that. And so we've got to rethink how we're building these things if we want to get those advantages. And I'm a biased perspective on it. They've got to start teaming more effectively. If it takes 10 of me to run one of it, that's not teaming, that's micromanagement of a system. And so how do we reverse that? There have been programs that looked at scaling systems. We've got some sitting on the stage here. That's part of the issue. But the question about meaningful control is another one, which is, what are we doing with that system? What do we expect that system to do? What are the mission objectives of that system? And how can I leverage both the people that will be involved in the system and the automated components of that to get at that more efficiently and more effectively and more resiliently and more robustly? Those are the real challenges. I see a repeated pattern of building systems the same way, and you end up with this 10-to-1 ratio problem. We got to figure out how to break that. Otherwise, we're going to be outpaced pretty quick.
Yeah. Well, thank you sincerely. Thanks for joining the conversation here. Look forward to continuing the conversation, but thanks for being thought leaders in this domain. Appreciate your engagement within this community, but just the autonomy community writ large, both platform, human, and hardware, software. But thanks again for also helping us see farther, but also realize what we have here. Thanks.
Thanks, Phil.
Cheers.
Cool. Thank you.
Thank you for joining us this morning.